One of the really cool things about this problem is that you may have parameterized it in different ways and you should get the same answer. So the problem was to calculate this scalar line integral of the function f of xy equals 3y over the portion of the curve y equals 2x from 1, 2 to 9, 6. So that looks like this kind of, and here's the point 1, 2, and here's the point 9, 6. And so you want to compute it over this. And so you can think of it as sort of being a fence, the same kind of fence as before. The higher you get in y, the higher the fence is. So it starts at height 2 and it ends up at height 6 over this thing. And I think we know that what we should do is that it's like the area of the fence. It's the integral from t equals something to t equals something, t equals b, of f of x of t times the magnitude of x prime of t dt. So the idea is that this is like the speed, this part is time, so this whole thing is distance, and then this other part over here is like height of the fence. So at each little increment of time, we say how far we've gone, and then how high the fence is. And so height times distance, that's width times height, it gives you area, you add them up, you get the area. At the first time we wrote down this equation, a lot of you complained. You said, the speed of the fence? What do you mean the speed of the fence? It's just a fence, it doesn't have speed. But the idea is that depending on how you parameterize it, the speed would come out differently. And yet the answer should come out the same. So for this one, there are several ways, like I guess infinitely many ways to parameterize it, but let's just talk about a couple of them. So we could have, could I have yellow? Let's see, I think it's yellow. I'm trying to get different colors that you can see. So one way to do it would be, let's see. So we'll do x of t. Our parameterization is x of t, y of t. We have some options. We could just say, well, I'm going to have my x be t, and then y is 2 times root x, so my y should be 2 root t. Perfectly good way of doing it. Alternatively, you could use, so not the same, but alternatively, you could be like, I don't like square roots. I'll say that, I don't like square roots. So I'm going to have x be t squared and y be 2t. Let's see, does that work? If x is t squared, then square root of x is t, so y is 2t. So that seems to work. And an alternative way of doing it would be to say, well, y is going to be my t, and now I have to figure out what x is. I think it's t squared over 4. Let's see if that works. Y is supposed to be 2 times the square root of x. We take the square root of this, we get t over 2, we multiply by 2, and we get t. Okay, so these are 3 different ways of parameterizing the curve. And probably there are 3 of you in the room that did, like, maybe all, is there another way that someone did it? No, you all picked one of those ways? Okay, and we're going to write out 3 different integrals, and they should all come out equal. So the area, let's see. Let's do the first one. So for the first one, we want to go from t equals something to t equals something. Okay. So let's see. What are the t's should be to get the whole curve? So x is t, so we just go from x value to x value. So this should go from t equals 1 to t equals 9. Then we need f of x of t. So f of x of t, we'll just remember up here, is 3y. So that's 3y, so that's here that should be 3 times 2 root t. Oh man, now we have to find our derivatives times the derivatives. I guess I'll try to do this in my head. Did anybody do this one? This is 1. This thing squared is 1. And you have it over here. 1 over square root of t squared dt. So that comes out that way. Okay? How about if we do it with the orange parameterization? I'm writing equals because they should be the same. This is not a simplification. This is another way of doing it. So for this curve, x is t squared. So if, let's see, I think t should go from 1 to 3. those should get us the x's that we want. If t is 1, x is 1, and y is 2, that works. And if t is 3, x is 9, and y is 6, that works. So that should be good. Our function is 3 times y, so 3 times 2t. And then this thing, the derivative with respect to x is 2t, so we get 2t squared. And the derivative with respect to t is 2, so I think we get 4 dt. Tell me if I make a mistake. Did I make a mistake? Because very possible I could make a mistake. But that should work. Okay, and finally, with this parameterization, our t-value is just y, so y goes from 2 to 6. So this should go from t equals 2 to t equals 6. Our function is y, so 3 times y is 3 times t. And then the derivative of this, 2t over 4 is t over 2. So we get t over 2 quantity squared plus the derivative of this is 1 squared dt. So I think these integrals should all come out the same. So that's the wonderful thing. Notice that these speed functions are all different because you parameterize them differently. For this one, the fence is going at a constant speed in the x direction, so that means that it's sort of going fast in the y direction at the beginning and very slow in the y direction at the end. This red one is going at a constant speed in the y direction, which means it's going slow in the x direction at the beginning and fast in the x direction at the end. But it's okay, the speed thing adjusts for that. And you might find, if you tried to do these, that they would be different amounts of hard. This one comes out to something like the square root of 1 plus t, integrating the square root of 1 plus t. You can do that. This one, you integrate t on the outside times t, the square root of a t squared thing on the inside. So it just depends. It's like maybe a little bit more involved u substitution than the other one. So they should all come out the same, but they're like different calculations.